In this section, we're going to talk about section 2.1 population models. And if you'll recall, we actually already discussed one of the more basic population models back in section 1.4, which was the population growth, assuming constant birth and death rates. And so what we were looking at was this differential equation right here, dp dt equals kp. And we solved that as a separable differential equation to come up with the solution, which most of you are familiar with as the PERT formula. In this case, we're using k instead of r and p naught to indicate the initial population. It turns out that this model is good in some circumstances, such as exponential growth and decay of bacteria or compounding interest, but it doesn't capture all of the information that we might want in looking at various population models. And so in this section, we're going to talk about two other population models, the first being the general population equation, and the second being the logistic population equation. I'm splitting this section up into two separate videos because it's rather lengthy and the problems take quite a bit of time. So we're going to cover pages 1 through 3 of the notes in this video and pages 4 through 6 in a subsequent video. So to begin, let's take a look at the general population equation. We're going to assume a birth rate function b of t and a death rate function delta of t. I should say beta of t and delta of t. Then the general population equation is described by the following differential equation. So we have the rate of change of the population with respect to time is going to be the birth rate minus the death rate, because of course we add births and subtract off deaths, and then times the population there, p. So this models the change in population as a function of time t. All right, so to illustrate this general population equation, we have problem 10 from the textbook. It says, suppose that the fish population P of T in a lake is attacked by a disease at time T equals 0, with the result that the fish cease to reproduce. In other words, our birth rate here is 0. We have no new fish being added to the lake. And the death rate, delta, in deaths per week per fish, is therefore thereafter proportional to 1 over the square root of p. So let's go ahead and express that. The death rate, delta of t, is proportional to, so introduce some constant of proportionality. Generally speaking, we use k, proportional to 1 over the square root of the population. And if you want, you could bring that square root up with a negative exponent and write it as kp to the negative 1/2. And then just make sure to introduce your constant of proportionality. So I'll just write for some constant k. All right. And then we have, if there were initially 900 fish in the lake, so the population at time 0 were 900. And 441 were left after 6 weeks. So I'm going to let T be the number of weeks, 441. How long did it take all of the fish in the lake to die? This is a real uplifting problem here. So we are seeking the time, that is, how many weeks will it take in order for the population P of T to reach 0 fish. Okay, so let's set up our differential equation using that general population equation. So we have dp dt equals our birth rate, which is 0, minus our death rate, kp to the negative 1/2, times the population p. And so this simplifies to a negative kp to the 1/2. We recognize this to be a separable differential equation. So if I divide that p to the 1/2 over to the left-hand side, I am left with a p to the negative 1/2 dp. And then of course, moving that dt differential over to the other side, we have a negative k dt. So we can integrate directly here. This becomes a 2 square root of p equals a negative kt plus some constant of integration. Now, at this point, I could solve explicitly for p just by dividing by 2 and then squaring both sides. But honestly, there's absolutely no gain in doing that. They did not ask me for the solution of this differential equation. Rather, remember what we're looking for. We're looking for t. So I'd rather not obscure T by solving for P. T is fairly out in the open right now. So um, don't work harder than you need to. That's the moral of this story. Okay, so now let's use some of our initial conditions. We know that P at time 0 is 900. So what that gives me is 2 times the square root of 900 equals C. In other words, 2 times 30 or 60. So what I now have is 2 times the square root of P equals negative KT plus 60. We were able to solve for our constant of integration, but we still haven't solved for our constant of proportionality. So let's use that second initial condition there that says after 6 weeks, there were 441 fish. So that says that 2 times the square root of 441 equals a negative 6K plus 60. So the square root of 441 is 21. So 2 times 21 is 42. And I have my negative 6K plus 60. So if I move things around, I have 6K equals 18. So K equals 3. All right, so to recap, what we have is 2 times the square root of P is equal to negative 3T plus 60. All right, so here again, I'm not even going to spend the time to solve explicitly for P because I'm looking for T. Remember, our goal is T equals what when the population dies out. So I'm just going to replace P with 0, and I'm going to solve for T. All right, so the left-hand side is 0, 3T equals 60, so T equals 20 weeks. It will take this population of fish 20 weeks to go extinct in this lake after their birth rate dropped to 0. All right, so again, this is just an application of the general population equation. We're going to introduce one more population equation known as the logistic equation. So we have a definition here on page 2. It says if the birth rate function is a linear decreasing function of the population P, that is, you can express it in this format here, beta naught minus beta 1P, for some beta 1 and 0 positive. And if the death rate is constant, then the general population equation becomes precisely this, okay? So what I want to point out here is this set of parentheses here. This is just the birth rate minus the death rate. It's just that we have expressed the birth rate in this format and the death rate is constant. So this really isn't different from the general population. It's more of a very specific variation where we have this kind of a setup with the birth rate and the death rate. And so what you'll notice here on this second equality is they're rewriting this in terms of P and P squared. So if you distribute this outer P inside, you're going to have one quadratic term and one linear term, and then they're just writing those coefficients as sum A and B. So here again, this is called the logistic equation. Quite often we factor one of the P's out front and then solve it from here. You'll notice that this is also separable, but it's going to take a little bit more work to solve these types of differential equations as far as our techniques of integration. So let's take a look at an example that uses the logistic equation. Problem 26 from the textbook. We have a population P of T of small rodents has a birth rate beta of 0.001 P births per month per rodent and a constant death rate delta. If our initial population is 100 and it's changing at a rate of 8 rodents per month, how long in months will it take this population to double to 200 rodents? So let's write out what we have here. First, let's set up our differential equation. If we just think of this in terms of the general population equation, beta minus delta P, our birth rate is 0.001 P. Our death rate is some constant delta. and then we want to multiply by p. But here again, this is just an example of a logistic population model. And then the other information that we have is that the initial population is 100, and it's changing at a rate at t equals 0, it's changing at a rate of 8. Okay, so we're gaining 8 rodents per month at time 0. Okay, so our goal is to do what? It says how long will it take for the population to double? So t equals what for our population p of t to equal 200? So here is our goal. All right, so this problem is unique in the fact that we are given an initial condition on the derivative. Whenever you're given that, you want to use that initial condition right out of the gates before you start integrating, because once you start solving, your derivative goes away. So let's impose that initial condition right out of the gates. So dp dt at 0 is equal to 8. But according to our differential equation, that is 0.001 p of 0 minus delta times p of 0. So anywhere where we have a t, which is implied in p and its derivative, we're plugging in 0. So now I actually have to use the other initial condition. I'll highlight that in green, and we're going to plug that in here and here. And here again, we already plugged in the yellow initial condition. So in other words, we have 8 is equal to 0.001 times 100 minus delta times 100. All right, so if I multiply by 100, I'm going to move the decimal 2 spots. And then let's multiply that second 100 in. So that's going to give me 10 minus 100 delta. All right, so shuffling things around here, I have 100 delta on the left equals 2 on the right. And so solving, I conclude that delta equals 1/50th. So I'd like to plug that back up into my original DE, and I'm going to rewrite this 0.001 as a fraction. So instead of 0.001, I'll write that as 1/1000th. So I have 1/1000th p minus 1/50th times p. And then just to simplify things a bit, let's multiply both sides by 1000. So we have 1000 dp dt equals p minus 20 times p. So this looks a little bit nicer without all the fractions. All right, so we are now in a position to separate variables to solve this differential equation. So I'm going to shift all of the p's over to the left-hand side. I'm going to leave the 1000 out as a coefficient. I have dp on top and p minus 20 times p on bottom. And here on the right, I just have dt. All right, so we need to recall our knowledge of techniques of integration here in this problem. And what we see is a rational function with linear factors here on bottom. So we would like to proceed by splitting this up here into partial fractions. So we're dealing with linear factors. They each get a coefficient a and b on top, and we want to split those up. Now, it doesn't matter which term you stick with A and which one goes with B. So if you want to flip your A and B, that's perfectly fine, right? Your A can be my B. And so now what I'd like to do is equate the integrands. That is 1 over P minus 20 times P equals A over P minus 20 plus B over P. And to simplify this and solve for A and B, I'm going to multiply both sides by that common denominator, P minus 20 times P. And so that leaves me with a 1 on the left and an AP plus B p minus 20 on the right. And so choose convenient values for p to solve for a and b. So for example, if I let p equal 0, then my a term drops out and I get 1 equals b times negative 20. So b equals negative 1/20th. And similarly, if p equals 20, that will allow my b term to drop out. So I get 1 equals a times 20, or a equals 1/20th. Okay, so now what we would like to do is we'd like to take these two values and plug them in up above to our integral. Now I'm going to just go ahead and, oops, I just noticed up here, I'm going to write it in red. I did not include my 1000 over here. So make sure you don't lose track of that 1000. But what I'm going to do is I'm going to pull that 1/20th out front, so that I'm not carrying it through. So I have 1000 and now divided by 20 out front. And then that leaves me with a 1 over p minus 20 plus, actually, negative 1 over p in back dp. And then, of course, I still have my integral of dt. So now that we have split up by way of partial fractions, we can go ahead and carry out the integration. 1000 divided by 20 is going to be 50. So I have a 50 times the natural log of the absolute value of p minus 20 minus the natural log of the absolute value of p equals t plus c. Now I'm going to go ahead and combine those natural logs just because it'll be a little bit more compact. I have 50 natural log of p minus 20 over p equals t plus c. So here again, recall that we're trying to solve for t. There is absolutely no sense in dividing by 50 and applying the exponential function and doing a bunch of simplifications to solve for p of t. Had they asked to solve the DE for a general population formula, fine, we would do exactly that. But in this particular case, they don't ask us for that, so let's not work extra hard. However, we do need to solve for this constant of integration. So I'm going to use the fact that the initial population was 100 and plug that into what I have currently. So 50 times the natural log of 100 minus 20 over 100 equals 0 plus c. All right, so let's see, what is this? 80 over 100, this is just 4/5. So we now know what c is equal to. And so let me recap. T is 50 natural log of p minus 20 over p. And then I'm going to subtract my constant over. So that is a 50 natural log of 4/5. I'll drop the absolute value since I know that to be a positive number. All right, and then finally, we're looking for the time it's going to take for the population to double to 200. So t is what when p of t is 200. So I've already isolated t. Let's just go ahead and plug in 200 for our population. So 200 minus 20 over 200 minus 50 natural log 4/5. I'm going to just pull this 50 out front. 200 minus 20 is 180. So 180 divided by 20 is 18 over 20 is 9/10. All right, and certainly you could plug this into your calculator right here. I just like to simplify. So I'm going to use that same logarithm rule that says the difference of two logs becomes the single log with the quotient. So that is 9/10 divided by 4/5, or the same as multiplied by 5/4. 5 goes into 10 twice. So this is 50 natural log of 9/8. All right, so now we can punch this into our calculator to get out a decimal value. And this comes out to about 5.9 months. All right, so in a population beginning with 100 rodents, after just shy of 6 months, that population will have doubled. All right, so this was an introduction here to the logistic equation. We're going to continue our studies on the logistic equation in the next video, as well as discuss things such as doomsday and extinction.